Hello and welcome to the combinational conversation piece. For this conversation piece, I designed a circuit that can do the dot product and cross product of two vectors. I made them signed 2's complement 4-bit vectors. And we will look at each of these circuits individually to see how they were built, and then I will demonstrate it here. But before we do that, I just wanted to go over what both of these are. So if I have two vectors A and B with these components, let's do one by hand just so we could make sure that we will have the correct answers. So basically for the dot product, which is this one here, you would multiply the first components in each of them, the second components together, and the third components, and then add the totals together. So here we got 1 times 2, which would be 2. Then we've got 2 times -3, which should be -6. And then we got 3 times 4, which is 12. And if we add those up, we should get 14 minus 6, which equals 8. And then for the cross product is a little convoluted. But if we have this matrix here, we can take the determinant of it by multiplying the diagonal. So I got I times 2 times 4, and then we have to take the other diagonal, 3 times -3. So 2 times 4 is 8. Then we have to subtract 3 times -3, which would be a plus 9. And that will be the ith component. And then we've got to subtract whatever the jth component is. So that will be j times 1 times 4, which is just 4. And then minus that from 3 times 2, which is 6. That will be our jth component. And then we'll add on the kth component, which would be 1 times -3, which is -3. And 2 times 2, which is 4. And if we do all of these, we should get 17i, and then we'll have a -2, which just becomes a positive 2j. And then I forgot the k over here. We've got the -3 minus 4, which should be a -7k. So now let's look at these individual components here. So to build the dot product, we have multipliers and then adders that add up each of these. The multipliers look like this. If you read the website, you can see that I did not watch the videos beforehand. So this is an 8-bit or a 4-bit 2-component multiplier, which ends up with 8 bits when you do signed extension, which is the way I implemented it. So you have this big circuit that gets repeated multiple times. Here's it zoomed up on one little section where you're adding up the 8 bits. So each one of these is a full adder. And then the adder you're familiar with. We've done it in class quite a bit. And that gives us the dot product. And then the cross product has the multiplications for each of the diagonals. So there's 6 of those, and then each one goes to a subtractor. The jth component needs to be negated, so I also have a negator here where I just did an adder and added 1 to it and negated all the inputs. I did try to implement a 3x3 matrix multiplier, but if you've read the website, you would know that once I did the custom look in LogiSim, it actually broke everything. So this is what it was looking like right before it was stopped working, and then when I did the designs, it kind of messed up everything, like you can see here. And for some reason, I've noticed this in LogiSim quite a bit, but this should be a gray line because it's not going to anything useful, or it should be at least red because there's no ground or power connected to it. And if I connect this one, for some reason it turns red, even though this is a single wire that doesn't go to anything else. So that is kind of weird, but that's all right. We still got the cross product and the dot product here. So if we do that same calculations from before, I should hopefully get out the same thing. So I'll put in 1 for my A vector, 2 for my or 1 for my ith component of my a vector, 2 for my jth component, and 3 for my kth component. And then if we go over to the b, we'll have 2 for that, and then -3, which is 1, 1, 0, 1, because this is 2's complement, and then 4. So if we look here, this is 8, which is what we got before in the dot product. And then if we come down here, another one of those weird things, we have an error randomly in this carryout, but luckily the carryout doesn't matter too much in the cross product. But we've got 1 plus 16, that's 17, and we did get 17i. And then we have 2j, and then finally we have this negative number. But if we keep the first one and flip all the other bits, we would get 1, 1, 1, which is that 7. So this must be -7, which is what we got before. So that is my circuit. Thank you all for watching, and I can't wait to see all of yours. Thank you and have a nice day.